Okay guys, hello and welcome back to another video. Today we're talking about electrostatics and electrodynamics. Question 31 says three resistors are connected to a 20-volt battery with a constant supply, and one of the resistors is a variable resistor. Okay guys, so I've just provided you guys with two formulas on the left side of the page. As you can see, whenever three resistors are in parallel, you just have to add them in a fractional form and then raise them to a negative power. And whenever they're in series, you just add them normally. For example, if you got let's say a 1 ohm resistor here, and then that's in series with another 1 ohm resistor like this. Let's say this is 1 ohms and this is 1 ohms. The total resistance of these two is going to be 2 ohms. Now, the question is saying the resistance of the variable resistor is gradually increased from 0 to 5 ohms. Which graph shows how the current from the battery varies with the resistance of the variable resistor? Okay, so right now, this resistor here, this variable resistor here has a resistance of 0. And so we can find out what the total resistance of these two are by using the formula that I provided at the first. So you can say 1 over 5 gets added to 1 over 10, and it gets raised to the negative power. So what's going to happen here is in order to add these two, we can't use a calculator. So we either got to do mental math or we got to multiply this one by 2 and this one by 2 as well. So we get 2 over 10 plus 1 over 10. And that's 3 over 10. And if we flip the answer, because of the negative power, we're going to be left with 10 over 3. So that's the initial total resistance. Now, how can I find the initial current? Because the graph has the current on one of the sides and the resistance on the other. So the initial current can be found by simply dividing the total voltage over the total resistance. I found this from Ohm's law. If you don't remember, R is equal to V over I. This is a very famous formula for Ohm's law, and obviously you need to memorize it. So the total voltage here is 20 volts, and it gets divided by the total resistance, which is 10 over 3. And that's going to give us roughly a value of 6 amperes. All right, so that means that choice B is not correct because it starts with 2 amperes. C is not correct. D is not correct. It's either A or E. Now let's see. For A, as you can see, the graph gradually decreases its current until it gets to 0 at 5 ohms. This is highly unlikely, so I'm going to rule out A anyways. But just to be sure, I'm going to show you how you can find out whether E is correct or not. So eventually it gets to 5 ohms, right? So we can safely assume we're going to have a circuit that looks like this. This is the initial 5 ohm resistor. And now it's in series with another 5 ohm resistor. And we have the 10 ohm resistor here at the bottom, right? So what's going to happen is, in order to find out the total voltage of this, total resistance of this circuit, we can actually use the formulas we just learned. These two are in series, right? So we can safely assume that they have 10 ohms of total resistance, and then the two 10 ohms are in parallel with each other. So we can find out their resistance by saying 1 over 10 plus 1, so plus 1 over 10 again, and that gives us 2 over 10, and then we get 10 over 20, 10 over 2 if we flip the answer, because this has a negative power, and we're going to be left with a total resistance of 5 ohms. Now, we do recall that the total voltage was 20, right? So if I wanted to find the current at the end, we just have to divide the total voltage by the resistance. So we just have to divide the 20 volts of the battery by the 5 ohms of resistance, and that leaves us with 4 amperes. And as you can see, at 5 ohms of resistance, the graph corresponds with 4 amperes of current. So the correct answer is indeed E. Now, guys, keep in mind that these types of questions have a highly, chance of showing up on the Imat. You also see a lot of things from capacitors and just voltage and circuits in general. One thing you got to be remembering is the fact that for parallel resistors, they get added using that fractional and negative power way. And for capacitors is the exact opposite. So if capacitors are in parallel, they get added normally, like C1 plus C2 plus C3. But if they're in series, they actually get added with using the fractional way, like as if they were resistors in parallel. All right, let's take a look at question 32. It says, when cooled below 4.2 kelvins, mercury becomes a superconductor, which means that it has no electrical resistance, all right? And when current is passed through mercury under these conditions, which of the following effects will be present? Okay, so first of all, when there is no electrical resistance, there's no thermal effect, there's no heat. And because mercury is a single element, there's no chemical effect either. The only thing that will happen is there will be a magnetic effect, and in fact, there will be a stronger magnetic effect because superconductors actually create or generate stronger magnetic fields. So the only correct answer is D3 only. Now, let's take a look at question number 33. It says 3 identical capacitors are connected as follows. So let's, like I mentioned at the first question, these are capacitors, and capacitors, they kind of work the exact opposite way of resistors. So if this is C1 and this is C2 and this is C3, they're going to get added if they are in, actually in parallel, but they're going to get added using the fractional way if they're in series. So this one would be the smallest value because they're going to get added, in fractions and then get raised to a negative power. So they're going to get 1 over C1 plus 1 over C2 plus 1 over C3. But whatever the value of these 3 is of the third shape, they're going to get added normally. So C1 plus C2 plus C3. So if they're added in series, they're always going to have a larger value than if they're added, if they're added in parallel, they're always going to have a larger value than if they're added in series. And if, considering they have the same amount of capacitance, like each one has the same amount, like this one has 2 farads, this one is 3 farads, this one is 4 farads, the same goes for the first one. So it's saying which of the following shows the order of increasing capacitance, smallest first. So the smallest is obviously number 1, then it's 2, and then it's number 3. So D is the correct answer for 33. Let's go ahead and take a look at 34. In an alternating or AC current generator, a coil of wire rotates in a magnetic field. Which of the following would change the potential difference, or basically the voltage or the electromotive force, also commonly known as the EMF, in the system above? Okay, so obviously by using more turns of wire in the coil, that's going to increase the kind of the flux in contact with the rotations. And so that's going to increase the voltage. And using a thicker wire has no effect on the voltage. It could decrease the resistance, but it doesn't make a difference on voltage. Changing the speed of the rotation will also increase the flux in a way. And as a result, more flux equates to more EMF or more voltage. So 1 and 3 is the correct answer, which makes choice E the correct answer. 35, it says an earth magnet is near a bar of material which is seen to be repelled by a magnet. Which bar could the material be? Which could the bar of material be? Now, guys, a lot of people get confused on this question, but they don't realize that you just have to see whether something is magnetized or unmagnetized here. That's it. It says a bar of unmagnetized soft iron. Could that be attracting or repelling our magnet? Yes, but it's unmagnetized, so no in this scenario. No for the unmagnetized cobalt. Electrostatics have nothing to do with magnetism, and so we can also rule out choice C and E because electrostatics are about positive and negative charges, all right? We're talking about magnets here. We're talking about magnetism specifically, and it's kind of like a throw-off, but the real answer is D because it says a bar of magnetized steel. That's the only way that's the only material out of these that could be repelled by the magnet because it's the only thing that's magnetized. All right, let's take a look at 36 now. 36 is again about a circuit, and they're saying the internal resistance of the battery is negligible, thank God. And we just have to find the readings of Z, which is a voltmeter, X, and Y. Okay, so first of all, we have to find the equivalent resistance for this one. These two are going to be in parallel with each other. So we have 1 over 4 plus 1 over 4, and they get raised to a negative power. And 1 over 4 plus 1 over 4 is actually 2 over 4. And if we flip 2 over 4, we get 4 over 2. So the total resistance of that section is 2 ohms. And then these are in series with this 4 ohm, right? So 4 plus 2 is actually 6 ohms. So we can have 3 circuits just to kind of make it clearer for ourselves. We have the first circuit here. Let's call this one circuit number 1. The second circuit is when you have the 4 ohm resistor that's in series with the equivalent resistance of those 4 in parallel. So the 2 ohm resistor here and 4 ohms here. And then last but not least, the last circuit, you have a 6 ohm resistor here. That's in sort of series with the battery. So this is a 6 ohm resistor. Now, because it is 6 ohms and it's in series with the battery, it's going to have the same voltage as the battery, obviously. So it's going to have 12 volts. You can find the current running through this battery by dividing its voltage over its resistance. So 12 divided by 6, and 12 divided by 6 would give us 2 amperes. Now, we can take the current we found on the third one and go back to the last circuit. Whenever we go back to a circuit and it's a series circuit, you can take the current with you. So right now, because it's in series, these two are in series, both of them will have 2 amperes. And so you can use that to find their voltage. The voltage of this one is going to be the resistance of it multiplied by its current. Again, this is just from a rearranged version of the Ohm's law. So 2 times 2 will give us 4 volts as the voltage of the 2 ohm resistor. And for this one, it's going to be 8 volts. And look at the beauty of that. If you add 8 to 4, you get the total voltage of the battery, which is 12 volts anyways. All right, now we can take those 2 currents and those voltages back to our main circuit. Let's erase everything so it becomes a bit clearer for us here. Okay, so if we go back from 2 to the first circuit, this one is going to have a voltage of 4 volts, which means this one also has 4 volts. And it would have a current of approximately the current that it had when it was just a single one was 2 amperes, right? So that means both of them now have 1 ampere. You can actually find their current by simply dividing the voltage over their resistances. And the amount of voltage this 4 ohm would get would be the same as it was getting in the second circuit, because we're going back to a series circuit. So it's going to have the same current, which is actually 2 amperes. And it's going to have the same voltage. I mean, even if we calculate it, we'll find that its voltage is still 8 volts. And the current that will eventually go back to the battery is going to be equal to the total current that was going into the final circuit. So if like 2 amperes enters from here, then 2 amperes should go back to the battery. That's always the case, unless you have some component right before the battery or something that decreases the voltage or increases the voltage. So Y is going to have a reading of 2 amperes, which rules out choice D, B, and A. And the value for the ammeter next to 4 ohms, this one, is going to be equal to the voltage running through it, which was 1 amperes. How? Because its voltage is 4 volts and its resistance is 4 ohms. So you can find its current by dividing its voltage over its resistance. It has 4 volts and its resistance is 4 ohms. So that means it has 1 ampere. Now, how did I know that its voltage is 4 volts? I found it from the last circuit, the second circuit. And when I went back to the initial circuit, because it was a parallel circuit, I could take the voltage with me. So whenever you go back to a parallel circuit, you can take the voltage with you, and both the appliances or components will have the same voltage. And whenever you go back to a circuit and it's a series circuit, you can take the same amount of current with you. So the value for X is going to be 1 amperes, and the value for Z is actually 8 volts, which means choice C for this question is the correct answer. Now, these questions, they require a lot of practice because you need to kind of go around and find out how you can find these currents. And if you go back to, for example, a parallel circuit, what can you take with you or not? And there are some easier ways of doing this, but you need to learn how to analyze it because sometimes you cannot use the easier ways. Nonetheless, make sure you practice a lot on these types of questions. And if you have any questions by yourself, please don't hesitate to ask me on our Instagram or join our Telegram channel. We're soon going to open probably a discussion group, and you can ask and sort of talk about your questions there as well. Now, let's go ahead to question 37. It says a student has 3 6-ohm resistors that can be connected in any configuration. What are the maximum and minimum resistances that can be obtained by using one or more of these resistors, 3 resistors? Okay, so the maximum resistor is when all 3 of them are in what? They're in series. So you can just add the 6 to the 6 plus the 6, you get 18 ohms. That means choice C, B, and A are all wrong. The minimum resistance is when all of them are in parallel. So 1 over 6 plus 1 over 6 plus 1 over 6 raised to the negative power. That's it. That is when they're all connected in parallel to each other. So it looks kind of like this. This is when they're all in parallel. That's when they will have the minimum value. If you don't trust me, let's take a look and find out what's their value going to equate to. So if they're all in series, they're going to have 18 ohms. But if they're in parallel, their value is going to be 3 over 6, and then if we flip 3 over 6 because of the negative power, we're going to get 6 over 2, which is 2 ohms. So the correct answer is choice E. A resistor has a resistance of 5 ohms, and there is a direct current of 10 amperes in the resistor. What is the power dissipated by the resistor? This is actually a fairly easy question. I'm sure every one of you will do this if you know the formula for power. Power is simply going to be I squared times R. So that's current squared times the resistance. Now we know the current in this question is 10 amperes, and the resistance is 5 ohms. So it's going to be 10 to the power of 2 multiplied by the resistance, which is 5. So we're going to get 100 multiplied by 5. And that's going to give us 500 watts, which means choice E is the correct answer. Let's take a look at question number 39. Now, question number 39 is a question about electrical resistance of a wire, and you need to know the formula for this one. I'm going to write it down for you guys. So resistance is equal to rho L over A, which is area, and rho is the resistivity while L is the length of the wire. So L, or the length in this question, happens to be 2 meters. It says a wire of uniform resistivity. That means a rho of, let me write that down, a rho of 1 times 10 to the power of negative 6 ohms with a length of 2 amperes is actually what is being asked of us. And then the diameter of the wire is 2 times 10 to the power of negative 3 meters. So they're saying, what is the electrical resistance of this length of the wire? So they're looking for R, right? Now, we don't know what area is, right? Well, actually we do, because it's a circular wire. The area of a circular wire is always going to be found by using pi r squared. And we have the diameter, and we know that resistance is half of the diameter. So there is the radius, the radius is half of the diameter, not resistance. The radius in this question is actually 1 times 10 to the power of negative 3 meters. So we can find the resistance simply by saying rho is 1 times 10 to the power of negative 6 multiplied by the length, which is 2 meters, divided by the area, which is pi, times by r squared, which is 1 times 10 to the power of negative 3 to the power of 2. Okay, so if we were to kind of find out what that is going to give us, we're just going to get resistance is equal to 1 times 10 to the power of negative 6 multiplied by 2. And that gets divided by pi times 2 times 10 to the, times 1, my bad, times 1, because 1 raised to the power of 2 is still going to be 1. 1 times 10 to the power of, now this negative 3 and 2 gets multiplied, so times 10 to the power of negative 6. These cancel out, and you get the resistance is 2 over pi, which makes choice E the correct answer. Now, that is it for today, guys. I will leave another video on Coulomb's law, which is one of the only questions that was about Coulomb's law, for another day. Make sure you subscribe if you like these videos and if they're helping you out. Check out our channel on Telegram again. We have lots of PDFs that can help you and make you revise for the Imat. And make sure you follow us on Instagram as well. We have tons of